Hey everybody, welcome to our next lecture. Today we are going to talk about functions and problem decomposition. In other words, the process of taking a problem and breaking it down into its constituent logical parts and then using programming to write a solution on how to solve the problem. All right, so starting off, here's our main objectives for the day. First off, we're going to understand why these things called functions are essential for writing code that is clean and efficient and reusable, and also removes repetition. Okay, removing repetition is what makes our code cleaner and easier to understand, and so on. We're also going to obviously talk about what are the mechanics for creating a function in MATLAB and then calling the function and making use of it. If you recall our first lecture, we had a couple of functions that we made use of without actually talking about how to create our own. We used the disp function and we used the roots function. And a couple others. And so today we're going to focus on creating our own sort of user-defined functions. And then we'll talk about how to do what's called refactoring our code into a function. And we'll do this both manually, and then we'll also do it with the assistance of AI. All right, so let's start off first with the why of the problem here. So the problem of repetitive code. One of the main goals of an engineer is to, when we're making tools, we want to make sure that those tools are efficient and, if possible, reusable. Okay, so if you're building a drill, you want to be able to use that drill more than just once. Or if you're designing a car or a rocket ship in the case of SpaceX, you want those tools to be efficient, easy to use, and also able to be reused over and over and over again. Now, some things obviously you can't reuse, like certain stages in a rocket, for example, you just can't reuse them. There really isn't any reasonable way to reuse a satellite that's been launched into orbit or whatever. But, there are certain things like the boosters on a rocket, for example, that SpaceX has figured out how to land back on a floating drone ship in the ocean and reuse them. Okay. And so we're going to do, nothing that crazy and complex, but we are going to do something similar to that today with respect to programming. We're going to come up with a way to create code that we can use over and over and over again to calculate a very specific type of algorithm, and then you'll be able to do the same thing in your lab after lecture. Okay. So if you recall, like last time we did this creation of a tool, we solved the quadratic equation. And so the driving question moving forward then is, what happens if we wanted to solve a similar problem, but we wanted to do that similar problem over and over and over again? In other words, we wanted to create a little piece of code that would solve a very specific problem, and then we would want to, take that code and encapsulate it or put it into a storage container of some sort, so that we could just like feed that container inputs, and then out would come the result of the calculations. Okay, so we're going to set up an example of this here in a second. So let's start off just with a single instance of that problem. And so we're going to have our little challenge here be calculating our weight on another planet. In this case, it's going to be the planet Mars. All right. And so, as far as calculating our weight, we don't have to worry about how the math was created or anything like that. That's a physics problem. That's not a programming problem. All we need to know is what is the equation and what are the various variables or inputs that we're working with. So in this case, we have this equation down here highlighted in red. Your weight on Mars over your weight divided by your weight on Earth is equal to some constant times the mass of Mars divided by some other constant times the radius of Mars squared. Okay, that ratio allows us to calculate what our weight on Earth is. Okay, and so we're going to basically take this equation along with some pre-established inputs or initial values, in this case our weight on Earth, the mass of Mars, and the radius of Mars, and we're going to plug those into the mathematical equation, and we're going to get a result, and we're going to display it to the screen. Okay, so as you can see here in the script, it's pretty straightforward. We start off with a comment that says weight on Mars calculation, and then following that is a little bit of a note that describes what this notation in MATLAB means. So if you have a number followed by the lowercase e and followed by another number, that is what's called MATLAB's scientific notation. Okay, so that's equivalent to the value 6.4 times 10 to the 23rd power. Okay, so if you see a number like 3.4e6, that's actually 3.4 times 10 to the sixth. And so that's the radius of Mars in kilometers, presumably, and then the mass of Mars is 6.4 times 10 to the 23rd kilograms. Okay? And then Earth weight presumably is 150 kilograms, which, if I do the calculations, that's actually kind of heavy. So anyways, next thing we do here in our calculation after we have those initial values for our Earth weight and mass and radius of Mars is we calculate that ratio that we had on the right side of this equation. So 6.8 times 10 to the negative 12 is essentially the result of taking this big G and dividing it by little g. Okay, I don't care where those numbers came from. They're just numbers. They can be magic for all I care. But I know that when you plug them into this equation, all we have to do is multiply it by the mass of the planet, which in this case is capital M, divide it by the radius of the planet squared. And then once that's done, we have our little ratio value. And then in the next line, we multiply that ratio by our weight on Earth, which is called Earth weight as a variable name. That gives us a result, which we're going to call Mars weight. And then we're going to display the line of text, which says weight on Mars, colon. And then on the next line, we're just going to display whatever data is stored inside of that variable called Mars weight. Little side note here, you'll notice that we called the first weight Earth weight, just all one string of letters. And then for Mars, we called it Mars underscore weight. That's two different ways or two different what are called naming conventions. Both of them work fine for me. You might see other people use the convention of, it's called like a camel case or something like that, where you start off the variable with a lowercase and then every subsequent word that you create starts with a capital letter. So in the case of Earth weight, it would be Earth weight and the W would be capitalized and the E in Earth would be lowercase. Okay, so again, we don't have any naming conventions that we enforce in this course, but depending upon if you go to a well-established company or something, or if you take a course that really cares about style and things like that in your programming, you might run up against certain naming conventions that you need to satisfy. Okay, so now let's move a little bit forward. So the script that we did on this slide, very straightforward. It just calculated our weight on Mars, given our weight on Earth and the mass and radius of Mars. If we wanted to add in another planet, so let's say Jupiter, in order to do so, we would have to essentially gather the weight and the radius, or sorry, not the weight, the mass and the radius of Jupiter. And then we would have to recalculate that ratio. Because if you look at the equation down here, the ratio is essentially this constant number times m divided by r squared. And since the mass and the radius here are going to be associated with a new planet, in this case Jupiter, you're going to have to recalculate that ratio. So if you go over here to the code, you'll notice that sorry, I got a little ahead of myself there. You'll notice that we still have the code from before when we were calculating the stuff from Mars. So that's in the first half of this script. And then the second half of the script introduces a couple of variables for the mass and radius of Jupiter called JupMass and JupRad. And then it recalculates the ratio to a different value. And then uses that new ratio value to multiply by our original Earth weight, put it into a variable called Jup weight, and then display weight on Jupiter is whatever that calculation equates to. All right. And so the real issue, though, looking at this is that relative to the first version, which was just used for one planet, and now we have two, is that there's some repetition. Okay, there's some similarities here in the code, especially with respect to the way that the calculations are done. And so if we were to take this original piece of code here when we did it just for Mars and we wanted to add in another planet for Jupiter, the obvious way to do it would just be to copy the first part, right? Copy the calculation for Mars, and then paste that calculation down here for Jupiter, and then go through and change Mars mass to Jup mass and Mars rad to Jup rad, and then go through and make sure that we changed the Mars and values inside the ratio calculation to Jupiter values and so on. The issue with this is that the whole process of copying one piece of code and copying it elsewhere, and pasting it elsewhere, can be dangerous. Okay, as you can see over on the list over there on the far side. First, it's error prone. If you're not doing just a straight copy paste and instead you're actually typing in the copy, you might make a typo here and there. Or you might forget, for example, to change like change Mars mass and Mars rad in the ratio calculation to Jup mass and Jup rad, okay, after you've done the paste. And so that's technically a typo because you're using the wrong values to calculate the ratio, and you'll end up having your weight on Jupiter be the same as that on Mars because you're using the wrong inputs, so to speak, for the ratio calculation. Okay. It also just is harder to read. Like if you look at this version of the code and compare it to this version when it was just for Mars, there's just more code there and more places for your eyeballs to wander, and it's not as nice to look at. And it's also just in general inefficient. We're essentially telling the computer to do something multiple times in different places, whereas if we could sort of take that calculation or that set of instructions, and since it's very similar, put it in one place and then just change it a little bit so it works with different inputs and generates a different output based on those different inputs, we'd be better off. Okay, so there's got to be a better way here. Engineers, as it says in the list over there, they don't like to repeat themselves. Instead, they want to build a reusable tool. They want to build a rocket that you can launch into space and then catch on the way down and then repeat over and over and over again. They don't want to have to keep rebuilding that rocket or even more importantly, the engines that go into that rocket. Like those things are expensive to build, right? Millions and millions of dollars. And so every time you can reuse it, you're saving money. And in the case of programming, every time you reuse a piece of code or reuse an algorithm, you're making your code more error-free, easier to understand, and more efficient. Okay, so that's what we're going to do today. All right, so that was the why. Why are we doing this? Now we're going to talk about what. How are we actually going to do this? And we're going to do this using something called a function. All right, so a function has a couple of key traits associated with it. First off, it's one of these reusable tools that we've been talking about. It's a block of code that has a name associated with it so that you can call it. And it's intended to perform a specific task. And that task is set up in what's called the function's definition. So we'll talk about how to create a function definition here in a second. You're going to write these things once. Okay, you write the algorithm one time. You're not going to copy it and paste it all over the place. You're just going to write the algorithm in one place. If you recall, an algorithm is just a set of instructions for a computer to execute. And so we're going to write that list of instructions in one place, and then we're going to call it many, many times by giving it different inputs. So in the case of what we had here, we're going to create an algorithm that'll help us calculate our weight on a new planet. And the inputs to that are going to be the radius and the mass of the planet, and then the weight of the person on Earth. Okay, and then ultimately this is going to provide us a way to remove repetition and sort of address all of these issues that came up in the copy paste is dangerous part of our slides. Okay, so first let's talk about how to define or to write or create a function. Okay, so as I said, this bit of code is what's called a function's definition. And in MATLAB, it's not actually a script anymore. Okay, MATLAB actually has a special way of creating what are called function files that are different than creating script files. And this is something that is fairly unique to MATLAB relative to other programming languages that I've worked with in the past. Okay, if we switch over here to MATLAB, I can give you a feel for what this looks like. If you go up here to the upper left corner, we have a little button here that says New Script. New Script will allow us to create a new script. All right, and so let me hide Copilot for a second and all this stuff over here. So this is a script where we could type in things like a equals 2 and x equals 4, right? These are setting up variables and so on. One thing that I do want to mention, I forgot to mention it in our first lecture, is that this little semicolon that happens at the end of a line of code. Semicolons at the end of a line of code are kind of like periods at the end of a sentence, except in sentences we typically want to see those periods to denote the end of a sentence, whereas in MATLAB they're technically optional. Okay, so if we include them, if we include the a equals 2 and x equals 4 with semicolons after the end of them, what those semicolons do is what's called suppress output, or they don't write the result of the calculation to the command window. So if I were to take this little script here and hit the run button, the command window is not, oh, I got to save it first. Just a second. I got to save this to something. All right, I ran it. I called it untitled.m, right? And I ran it by essentially typing untitled into the command window. It ran the code, but we didn't see anything show up down there in the command window. The command window is essentially, empty. It's just the call to the untitled script, and then nothing came after it. But if you look over here in the workspace, you'll see that we have variables a and x stored with values 2 and 4 respectively, and so MATLAB did do the work, right? So if I go back here and I type in clear all, I can actually wipe out the workspace and reset it. So the workspace is empty now. And if I go back to my script and I remove those semicolons, one, MATLAB's going to warn me and say, add a semicolon to hide the output, okay? But I don't want to do that right now because I want to make a point here. So if I run this code now, what's going to happen is, it's kind of hard to see it, but let me see if I can stretch it up. There we go. Here's the untitled script name that ran the script, and then here's the output, a equals 2, x equals 4, right? The values still show up in the workspace. We have a and x equal to 2 and 4 respectively, but we also output the result of those assignments in the command window. Now, typically MATLAB does not like that, and that's why it's giving you this little warning here that you can hover over and it can tell you what's going on. In fact, you can even give it the option to fix it, and if you fix it, it puts a semicolon at the end and does it. But anyways, I just wanted you to know that in languages like Java, for example, or C++, those semicolons are necessary because it's a compiled language and they're kind of like, they have to be there or the compiler doesn't know that a sentence has finished. But in MATLAB, for the most part, they're optional. I would recommend just putting them in there regardless. And then if you want to display values, do something like disp a, like this. And then when you run the script, it just displays the value from a, which in this case is the number 2. It doesn't say a equals, it just says 2, right? That's what disp does. There's another function called display. If you're really wanting to get into the weeds of this, that it actually displays the name of the variable along with the value, but we don't need to focus on that right now. Okay, sorry. Anyways, bit of an aside there, but I thought it was a little bit interesting to talk about when you see these semicolons, what they're actually doing and why they're there. Okay. Oh, I should have stayed in MATLAB because I forgot what I was talking about. If you go to the new button here in the upper left, when we first opened MATLAB, it said there was a new script option, but the new button with the plus sign and this little new with a down arrow, if you click on that, there's actually several options here for things. The only things that we really need to focus on right now are script, which is what this untitled.m is, and function. Okay, if we click function here to create a new function, this will actually create a template function inside of another tab in our editor, right? And it has pretty much all the syntax that's associated with the creation of a like a default function. Okay, you could look at this if you wanted to, and you could break this down into its pieces and figure out what's going on. But I'd rather talk about it with respect to our slides, because the MATLAB function template's a little bit too involved for what we're actually doing. So right now, the only things that we really need to focus on when it comes to defining our own functions in MATLAB are essentially 3 things that we have to create, and then a couple of so-called default syntax that has to be there. All right. So first off, a function has to go inside of its own file. Okay. That's what the second bullet point over here says. Function definitions are typically written in their own files. There are some other types of functions called like nested functions and sub-functions and things, but that's something for another class and another day and another time. It's not for this. It's just way too much to think about. Right now, all we're doing is just writing one function that does one thing, or it has one algorithm inside of it, and it's inside of its own file, and its file name has to match the name of the function. Okay, so if you recall, these functions are these blocks of code that have names associated with them, and they have a specific task that they're intended to do. We write them once and use them many times, and they're reusable. And so in the case of the example here, you'll notice that at the top we have a little comment that says file name myfunction.m. So if we had this function defined inside of our MATLAB instance, it would show up over there inside of this untitled.m. Sorry, it would show up inside of that little file browser window over here on the left. It would be called totally forgot what it was. myfunction.m. So myfunction.m would appear inside of this little window over here, as a file, and you could click on it and you could open it and do whatever with it. So anyways, the important thing to note here is that the name of the file that contains this function is myfunction.m, and it's named that because the name of the function, as you can see, is myfunction. All right, so if you sort of extend these little next bits of comments down, these are supposed to be little arrows pointing down. The function name is myfunction, okay, and that means that it has to be inside of a file called myfunction.m. That's just convention. MATLAB expects it. It doesn't necessarily enforce it, but if you don't do it that way, things can go really weird and wrong really quickly. So just as a default rule of whatever, make sure that you always name your functions a functions file after the name of the function followed with the .m extension. Okay, it's really hard to explain, but it's really easy to do in practice. So anyways, all right, so once we get past all those comments, which, if you recall, are ignored by the computer doesn't care about any of the things that come after these percent signs. We then have the one keyword that tells MATLAB that this that this file contains a function, and that's literally the word function. Okay, so if MATLAB opens up a .m file and it sees the first real piece of text that it can use is the word function, it knows that this is a file that contains a function. Okay. After that is I'll use a word here that we'll explain later, but right now it's a vector of outputs, okay, or a list of outputs, and has a very specific syntax that's associated with it. It's a set of square brackets followed by the outputs, which there can be more than one, separated by commas. Okay, in the example that we have here, we have two outputs from this function. One's called out1, the other one's called out2. If you had three, you would just separate them by 2 commas. If you only had one output, you could put it inside of square brackets, or you could just leave it out of it. It doesn't really matter. There's all sorts of different ways to do this. I don't really want to get into the weeds too much on the different ways here. I want to just sort of focus on this particular example, but like I said, there's lots of different ways to do this. All right, the next thing that's required here is if your function has outputs, you need to have it followed by an equal sign. Okay, that list of outputs, or the vector of outputs, so to speak, has to be followed by an equal sign, and then the name of the function. In this case, it's called myfunction, and then after that is your list of inputs. Okay, inputs go inside of parentheses. All right, and this is very much like functions inputs for other languages like Java and Python and C++ and so on. The list of inputs to the function is inside of parentheses, and it's composed of what's called comma-separated list. And this is different than the list of outputs that occur as a vector. Okay, as I said, this is very confusing sounding, like as I'm hearing myself say, I'm like, wow, this is really confusing. But ultimately, just using it a few times, it just starts to make sense very naturally, especially if you've programmed before. All right. So anyways, after this first line of code that the computer actually cares about, it's also referred to as what's called the function's header, you then have the code that actually performs the task. Right now I just have it listed as a comment. So some code performing a task is going to go here. As far as the task is concerned for this little simple function, all it's doing is just taking the two inputs, in this case in1 and in2, and it's adding them together and multiplying them together, and then writing the result of each of those operations into the two outputs. So out1 is set equal to the sum of the two inputs, and out2 is set equal to the product of the two inputs. All right. And so this is the way that MATLAB generates output from a function. If you've programmed in other languages like Java, for example, you'll know that there's this special keyword called return. And return is used to return data from a function back to wherever it was called from. Okay, that's not in MATLAB. In MATLAB, in order for you to generate output inside of a function, you have to write values to the output variables, or as the comment says here, you have to assign results to the outputs. And if you don't do that, the function is not going to work right. Okay, and finally, every function has to have this special keyword at the end called end, like literally the word end. Every function needs it. And if it's not there, MATLAB might complain, or it'll put it in there for you or whatever, but like you need to have it there. It's kind of like a bookend to all the stuff that's in between. Like bookends typically have like a bookend on the left and a bookend on the right, and then you have all the books in between them. As far as a function is concerned, the left bookend is the word function and the right bookend is the word end. All right, and then everything in between those two keywords is the function. It's list of outputs, it's name, it's list of inputs, it's what's called the function body, the stuff in the middle here, that's called the function body. All right, so you have to start it with the word function and end it with the word end, and then save it in the right file name, and then you're good to go. All right, so how do we actually, now that we've written this little simple function, how do we call it? Okay, so a function call is basically utilizing that code that, as we said before, that has a name, that performs a specific task, and is written only once but can be called many times. A function call allows us to use that code repeatedly over and over and over again. Okay, so we defined it inside of myfunction.m, and we're going to call it, at least in this case, inside of or from the MATLAB command window. You can actually call functions from within scripts. You can call them from in other functions and so on. Right now we're just going to focus on sort of the bare bones implementation, which is calling the function from within the command window. All right, so just imagine that we have an instance of MATLAB running right now. This is what the command window would look like. Okay, you start off with creating a little vector, these val1, val2 variables inside of square brackets. We'll talk about vectors later on, but for right now we're establishing a list of values, and in this case the list has two elements inside of it, or an array. If you've programmed before, it's kind of like an array. All right, the word that MATLAB uses though for this is a vector, or an array actually, or a matrix. Really, lots of vocab. It's coming soon, but not today. All right. So, anyways, we established this two element array or list or matrix or vector, whatever you want to call it, and then we set it equal to the function call. In this case, it's the name of the function followed by a set of parentheses with values that are sent into the function as inputs. If we look back at our function definition up here at the top, you'll notice that our function definition has two inputs. They're called in1 and in2. If you go down to the command window, what's going to happen when MATLAB runs your function, okay, or calls your function, is it's going to take that 3 and it's going to store it into this in1 variable, and it's going to take the 6 and it's going to store it into the in2 variable, and then it's going to run the code inside of the function, and then it's going to generate its little vector or list or matrix of outputs, and it's going to assign that to the vector that we created earlier that has val1 and val2 inside of it. Okay, and then if we want to see what's inside of those two values, we can use the disp function like we talked about last time. So we do disp val1 and we get a 9. If we do disp val2, we get 18. All right, so that right there shows us what happened as a result of calling our function definition and generating the outputs and then assigning them to val1 and val2. All right, now there is one important thing that I want to talk about that's connected with functions, and this is a topic that spans like pretty much all programming languages, and that's something called scope. All right, I got a little quote there. It says, "What happens in the function stays in the function." Okay, now this is something that is a little bit different for every programming language, but for the most part, this rule of what happens in the function stays in the function is true. Okay, so the way it works, at least in MATLAB, and as I said, this is very similar to a lot of other programming languages, is that A function has what's called its own private workspace or its own scope. Okay, we've talked about workspaces in MATLAB. You know, it's the thing in the bottom left down there. Right now, our workspace has variables a and x with values 2 and 4 inside of them. Those are like the highest level values that are in the workspace. Like, you know, MATLAB is just sitting there waiting for me to do something, and it's got this workspace. That's like the top level workspace. But each function has its own private workspace that when the function's code is running, okay, when after the function is called and MATLAB is running the algorithms that are inside, the function has its own private workspace and it can't see the workspace that's on the outside. So if we were to call my function here and we had this external workspace that you can see down there with variables a and x inside of it, the function is not going to be able to see those external variables. It's only going to be able to see what the second bullet point here is talking about, which is the variables that have been passed in essentially as inputs. Okay, so if we go down to our little command window in this example here, you know, it's got more code in it than the command window from before. Before it was just a simple function call and then display of the two outputs. But here we establish two different inputs separately in the command window. So inval1 and inval2, those are equal to 3 and 6. Okay. If we had our little workspace open in our MATLAB window, we would see a pair of variables in there, inval1 and inval2, and they'd have values 3 and 6 associated with them. Then we do the function call here to my function, and we provide inval1 and inval2 as the inputs to the function. Now what MATLAB's going to do is it's going to actually take inval1 and inval2, and it's going to read the values that are stored inside of them in the main workspace. In this case, it's the numbers 3 and 6 respectively. And it's going to store them inside of the function's private workspace for in1 and in2. Okay, so the function is going to start executing, and its little private workspace, once the function starts, is going to have an entry for in1 and in2, and it's going to have values of 3 and 6. But the function itself is not going to have variables inval1 and inval2 inside of its workspace. Okay, it has its own private workspace, and it can't see the workspace that's outside of it. Okay, so anyways, as the function executes, it's going to take those internal private variables in1 and in2. It's going to do some calculations and write to out1 and out2, which, by the way, are also private to the function's workspace. And then it's going to copy those results back out to the command window into the location, or into the variables outval1 and outval2. All right, and so if you, after this function call inside of the MATLAB command window, after it's finished and we've assigned values to outval1 and outval2, there's actually going to be 4 variables living in the workspace that's associated with the sort of the highest level of the command window. Okay, it's going to be inval1, inval2, and then outval1 and outval2. Okay, and just to prove this to you, my camera's doing some weird focusing stuff. Hello, camera. There's my hand. There's my face. Focus on my face. Whatever. Sorry if it's blurry, it's blurry. Anyways, I'm just showing you that like disp inval1 results in a 3 being output, and disp outval1 results in a 9 being output. But if I try to disp the values or the variables for in1 and out1, they don't work. Okay, I end up getting some error messages that say unrecognized function of variable in1, unrecognized function of variable out1. And that's basically saying that like MATLAB doesn't know what those functions are inside of the command window because they actually existed inside of the function's private workspace, and the command window can't see that private workspace. And I could extend this too. I could put some disp functions inside of my function and try to disp like inval1 and outval1, and it would get confused there because the function can't see the workspace that's associated with the command window. Okay, so anyways, it's a rather complex concept. It takes a little while to get used to it. But over time, you start to understand like how scope works and so on, and it gets a little bit easier to figure out. Okay, so now let's talk about how to do something called refactoring functions. All right, so what is this? We basically want to turn that repetitive code that we had earlier. Remember, we were talking about Mars and Jupiter and the weight in Mars and weight in Jupiter and all that kind of thing. And we want to take that repetition and we want to put it inside of a function. Okay, in particular, a function that's going to calculate our new weight on any old planet. And so the way it's going to work here is we're going to create this function, and the function is going to be used to, perform a task, a single task. In this case, it's going to be to calculate a person's weight on another planet. And that function is going to take as input the weight of the person on Earth, and then the specific planet that we're thinking about's mass and radius. Okay? So in other words, the function is going to have three inputs: Earth weight, planet mass, planet radius. And depending upon what values we pass into that function, it's going to generate different outputs. If you've worked with functions before in other programming languages, you're like, duh, this is the most obvious thing in the world. But if you've never programmed before, this is a really hard concept to wrap your head around sometimes, because especially with the whole concept of scope that we talked about in this last slide, it can be a little bit challenging, like understanding that like the function can behave differently depending upon what inputs are sent to it. Okay, so anyways, with our new weight function, what we're going to do here is we're just going to write a function using the same sort of stuff that we had talked about before with respect to writing a function. So up here in the top, might be a little bit hard for you to see, but we have a file. It's called newweight.m or new_weight.m. And it starts off with the word function, and then it has a single output. In this case, the output's variable is PW. Then we have, excuse me, then we have the equal sign, excuse me, and then we have the name of the function, which is new_weight. And then we have three inputs. The three inputs that we talked about all the way right here. Oh, God, it's on the same slide. All right, so EM, PM, and PR, right? So the Earth weight, the planet's mass, and the planet's radius. Those three inputs, they exist only inside of this particular function's private workspace. If you remember our discussion on scope, those three inputs are then used, first the mass and the radius, to calculate this ratio, and then the Earth weight multiplied by that ratio to get the person's weight on that planet, which is PW. And that's it. That's all we have to do. We just take those three inputs, we can just assume that they have values stored inside of them because of the way that function calls work. And we can write to the result, PW, and then we're done as far as the function's definition is concerned. All we have to do now is actually use those functions inside of our original script to remove all that repetition. So we'll start off that script down here. We have Earth weight equals 150, Mars mass and radius, Jupiter's mass and radius. Those are all just like constant values, so we're storing each of those inside of associated variables. Then we call our function. The first time we call our function, we're going to feed it the inputs Earth weight, Mars mass, and Mars rad. When MATLAB runs this new weight function or calls it the first time, it's going to take the Earth weight, copy it into EW, Mars mass into PDEM, and Mars rad into PR. And then it's going to calculate those values using the internal private workspace of the new weight function. It's going to write the result into PW. And then the function is going to return back to our original script. And it's going to take that PW value, whatever it is, whatever's stored in it, and it's going to overwrite or write to this MW variable. In this case, the MW variable stands for Mars weight as opposed to JW later, which is Jupiter weight, or PW, which was planet weight inside of the function. All right, and then we just disp MW and we're done for Mars, and that's going to display the value of our weight on Mars. Now, if we want to do the same thing for Jupiter, unlike before when we had this big mess of repeated code, right, that had like the same multiplications and divisions and exponentiations and all that kind of a thing, all we have to do here to do the same thing is make another function call. So here we have new weight with Earth weight as the first input, But now instead of passing in Mars mass and Mars rad, we're passing in Jup mass and Jup rad. So the mass and the radius of Jupiter. And those values are going to be sent into the function, copied into the relevant like inputs, in this case PM and PR. The ratio is going to be generated. It's going to be a different ratio value this time because we gave it different inputs. And then the value for PW is going to be different as well because the value for ratio is different. Okay, the value for EW stays the same, the earth weight, but that's not really the important thing here. So anyways, the resultant calculation for PW this time we make the function call is stored into JW and then displayed to the command window using the disp function. So the thing to note here now is look how much cleaner our main script is, right? This script right here, if you compare it to the one that we had before, it's kind of far back, but I'm going to go there anyways. Look at this version of the script with all that math, and then look at this new version of the script here with all that not math. Okay, there's a couple of function calls there, but all the math is basically encapsulated in one place inside of this new weight function. And so we've done essentially what we talked about before. All right, we have created a reusable tool that is a named block of code performing a specific task. In this case, is calculating a new weight. We only had to write it one time. We called it many times, in this case just twice. And we removed that repetition. We made the code that was originally really ugly cleaner. Okay, so that's called refactoring. We've essentially we took the original version, which was sloppy and messy and had repetition, and we refactored it. We changed it into something different that created the same outputs, but did it in a different way that in this case was nicer to look at. And it turns out, believe it or not, we can use AI to do the same thing. So that's what we're going to do here on this slide. So in this case, the process of returning all that messy and repetitive code is simply just going to be handed off to the AI assistant, in this case Copilot, and we're going to let it do its thing and see what it does. Okay, and then we'll compare and contrast it to how we did it and see if they're, roughly the same. All right, so let me jump over here to MATLAB. And whoops, I got to grab the code first. Give me a quick second here. So I'm going to take all this code and I got to grab the prompt too. That's a really important part. So I grabbed the prompt. The prompt, by the way, I probably should mention, it says refactor the repetitive code below into a function that calculates a new weight based on a planet's mass and radius. Now that prompt is very specific and it leaves a lot of stuff open to interpretation for Copilot. When I first put together this example, I was like, there's no way that this AI is going to figure this out. Like, how's it going to know what like new weight and mass and radius and all this business is just by giving it code? Well, it turns out it did it, and it did it really well. So I'm going to show you. Hopefully it works again. So I'm going to copy all this stuff. I'm going to switch over to the MATLAB view. I'm going to get rid of all this junk. We don't need any of this stuff anymore. I'm going to clear all to make our window nice and pristine. And then I'm going to open up our Copilot window. I'm going to close all that stuff so that we only see what's necessary. Go over to Copilot, paste, Command V, whatever, and hit enter. And we're going to see what it does. Okay, so there's our prompt. There's our messy code. MATLAB goes through, does some stuff. And let's actually just take a peek and see what it says. Because it doesn't just generate code, by the way. It actually describes it. Like, it uses English and stuff, like words, to describe what it's doing. So you can refactor the repetitive code into a function that calculates the weight on different planets based on their mass and radius. Here's a complete code example. So we'll get to that in a second. Let's look at the end. In this code, the calculate weight function takes the Earth's weight. That's a little bit odd. The Earth's weight. Not the weight of Earth, because that's what it reads. It really should say the weight of the person on Earth, whatever. If you look at my original prompt, it didn't actually mention that. My original prompt just said calculates a new weight based on the planet's mass and radius. So anyways, that's neither here nor there. The mass of the planet and the radius of the planet as inputs and returns the calculated weight on the planet. Okay, so that's a little bit more specific there. The main script then calls this function for Mars and Jupiter, displaying the results. Okay, so now let's look at this whole script here. So let me make this just a little bit bigger. All right, so we start at the beginning. We have our function right there at the top. Weight on planet equals calculate weight. So weight on planet, that's the output. It has one output. Notice it's not in square brackets because it doesn't have to be because there's only one input. Equals calculate weight. So that's the name of the function. Okay. If we were creating our own separate function file, we would want to take this code and stick it inside of a file called calculateweight.m, and then, you know, go from there. Then we have three inputs: Earth weight, planet mass, planet radius. So shocker, it's like pretty much the exact same thing that we had in the previous example that we created. Then it's got a little comment here: calculate the weight on a planet based on its mass and radius. It generates an additional temporary variable. In this case, it's gravitational constant. Sets it equal to 6.8 times 10 to the negative 12. Then it generates the ratio using that gravitational constant value multiplied by the planet mass divided by the planet radius squared. Then it takes that ratio, multiplies it by the Earth weight, sticks it into the output, which is weight on planet, and boom, it's done. Yay. It does exactly the same stuff that we did. If we go back to our view, let me see if I can get it brought up here real quick. Whoops. Here it is. So here's our code, and here's MATLAB's code. So notice that the function looks about the same. So our code, it was shorter because I had to fit it on the slide. So I had to abbreviate a lot of the variables. I couldn't give it good variable names. I used PW and EW and PM. MATLAB used like full-on good descriptive variable names. As far as the code is concerned, inside, it's basically a ratio calculation, and then multiply the ratio by the Earth weight, and boom, you got your output. They do the exact same thing. Okay, and then if you look at the main script, you know, my main script over here in the script editor, it sort of it had all of the all of the constants in one chunk, and then the function calls and outputs were in like their own separate chunks. MATLAB did it a different way. MATLAB had Earth weight all by itself, and then the planet's mass and radius for both Mars and Jupiter integrated into the part that called the functions. But other than that, I mean, it's nearly identical, right, to the solution that we came up with on our own. And MATLAB did it, in like 12 seconds. Actually, it was less than that, like 7 seconds or something. So from the perspective of like, is this AI tool useful? The answer is absolutely yes. Like it literally did the work that we did. It did it faster. However, we had to make sure that we gave it the right prompt. So if we go back to our prompt from before, we needed to make sure that we wrote the appropriate prompt, which is refactor the repetitive code below and blah, 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 blah. And then we had to give it the code that needed to be refactored. All right. You know, if you want, you can like experiment with this kind of stuff and see if you could just give it entirely like an English language description of like, write a function that takes a person's weight and a planet's mass and radius, and like not even give it code that shows it the calculations. It might be able to use its AI brilliance to actually figure out what the equations are and do it for you automatically. You know, it's every time I think that I've discovered something that AI can't do, it typically has a way of figuring out how to do it. And in this case, it would probably go out and find this equation somewhere on the web and then generate a function and stick it inside of a script or function file or something that would do all this for you. I don't know. It's really powerful what these tools can do. Okay. So in the case of what we just did, all we did is show how it can be used for refactoring code and removing repetition. All right, so to summarize everything we talked about, we basically showed that, you know, repetitive code is inefficient and error prone. It's not something that you want to do. It's something that you want to encapsulate away into a function definition. These functions are essentially the reusable tools that make our code cleaner and more modular, like broken up into pieces that you can like reuse. And we can write these functions ourselves, or we can use AI to help us. And moving forward, that's, you know, what I'm going to advocate. This is the first time I've ever done this type of teaching in M-Engine, so we might discover some new things along the way, but everything that I've done in my other courses and my own personal experience has shown that, AI is here to stay, and it's here to help us in a lot of really cool and interesting ways. And we just have to do it. And learn how to do it, because if we don't, everybody else is, and we're going to be left in the dust. So anyways, that's all I got for today. Next time you see me, it's going to be in person. Awesome. Yeah, we'll go from there. Have a good time in your lab. See you later.